Okay, hello, good morning and good afternoon to all of you. Today we have a wide range of participants from all over the world, starting from Asia, Europe, and also from America. Welcome to all to this webinar today. My name is Erik Brüderer. I'm responsible for the global sales of the TLT-Turbo GmbH. Along with me today is Mr. Florian Neff. He will guide you through the short journey through the fan aerodynamics by today's webinar. He will basically start with basic information like volume flow, pressure increase, resistance lines. He will give you an overview about the different performance graphs of axial flow fans and centrifugal fans. The end of the journey basically will be, we will give you an outlook about possible upgrades of performance of fan and also of ductworks, maybe also of silencer equipment. This is basically the scope of this presentation today. You all have been set it on mute during this webinar, but you still have the chance to write your questions into the webinar tool. And at the end, depending on the time we have, Mr. Neff will basically give you some answers. So then I will now hand over to Florian. I think have a good start and good luck, and then we will talk later on.
Yeah, thank you, Eric. Welcome everybody, wherever you listen right now, to this short journey through fan aerodynamics. As Eric mentioned, my name is Florian Neff. I'm the head of the aeroacoustic group within the R&D department at TLT-Turbo, and I have the pleasure to guide you through this short journey through fan aerodynamics. As Eric also mentioned, please participate through writing some questions into the chat function, and at the end, hopefully we'll have several minutes to pick some of the questions and hopefully I can answer them. So then let's start with the agenda. The agenda looks a little bit different than you might expect or you normally see. So there are no words, but nevertheless, I would like to start with, as also Eric mentioned, with some basics about volume flow rate and pressure rise, how this leads to operating points for fans, and how this correlates with resistance curves. Then proceeding to performance curves of fans, and so how can a fan adjust to this different kind of operating points or conditions, with a short definition of fan efficiency, and yeah, at the end, outlook of optimization potentials. It's also, I would like to encourage you to participate at our short questions we ask in between. So we do some survey questions, and that I think gives us a better understanding of what you're dealing with on your daily basis and what's you're interested maybe for further aerodynamic webinars. Okay, let's start with the basics, and that should be about volume flow rate and pressure rise. But even before we start with that, I would like to answer the question, the simple question, what is a fan? And I do not want to read all this text, so I give you several seconds that you can read it by your own, and then I will dive into it. So maybe you also heard that some laypersons sometimes say turbine to a fan, which is wrong in the sense of turbo machinery definition. So a turbine is basically doing the opposite of a fan. It's a fan is putting energy into the flow, whereas a turbine is getting energy out of the flow. So that's a small but important difference between a fan and a turbine. Now we're talking about fans, and I highlighted here two words, or let's say, first of all, our fans are operating with gas, and the two highlighted words, once again, is volume flow. So the fan, the purpose of the fan is to convey a volume flow through a technical plant, and it has to overcome some pressure head up, needs to provide some pressure rise in order to that the volume flow can pass through the duct system. So let's have a closer look to volume flow rate. What is volume flow rate? I mean, a theoretical and dry answer would be, well, volume flow rate is the derivative of the volume per time. Hopefully a little bit more vivid or clear is if you have a look at a cuboid that of course has a certain volume, and this volume can be calculated as the cross section A times a length S. Or if you assume now that this kind of cuboid would be a part of the duct system, with the cross section A, the volume flow rate which is passing through would be the result of A times the velocity with which the fluid is passing here through this cross section. And once again, the velocity times the period of time you're interested in is the result for the length of this cuboid. So basically, once again, the volume flow rate is the indicates the volume of the fluid which passes per unit time. And for incompressible fluids, such as, for example, water, we get to the continuity equation, which is then basically saying that the volume flow rate is constant in a duct system, no matter what the cross section might be. So in this case, if you look at the bottom on the right-hand side, we have a kind of duct system, and the cross-section changes from A1 to A2. Basically, the volume flow rate in point 1 is the same as in point 2, but since the cross-section change, the velocity will change accordingly. So for bigger cross-section, the velocity decreases. That's valid for incompressible fluids, but I told you our fan is operating with gas, and gas is normally compressible. So we need to add another term here to the continuity equation in order to make it true. So for compressible fluids, the mass flow rate is constant. And the mass flow rate is basically the product of the fluid density times the volume flow rate. I'm sorry for showing you all these equations, and it's not the last, but maybe you can keep in mind, and that's, I think, quite easy to understand, what goes into the fan will come out again. So what's every time true and valid for compressible or incompressible fluids is that the mass flow rate is constant, whereas the volume flow rate might differ due to the fact that the density changes from fan inlet to fan outlet. Okay, so hopefully that gave you a little bit better understanding for the term volume flow. Let's dive into the next point here, which is pressure rise. Before we clarify that, I think it's good to have an understanding what is pressure. Again, here a dry answer would be, well, pressure is the ratio of a force which is applied to a surface, so F divided by A. I think the most common pressure and the special case here is the atmospheric pressure we all feel, also right now. So the atmospheric pressure is basically the weight of the air is pressing on every wetted surface, so on my body, on the desk, everywhere. And I think you also know the typical value for atmospheric pressure at sea level. That's around 100,000 Pascal or 1 bar, if you would like to have another unit. Okay, so that's pressure. Now coming back to the fan. Well, when the fluid now is moving through a duct system and the fan is trying to convey this volume flow rate, the fan would recognize on this discharge side that there's a kind of counter pressure, which makes it hard for the fan to convey this volume flow. So this counter pressure is caused by pressure losses in the duct system. So there is friction everywhere, there are losses everywhere, nothing is without friction, and therefore these pressure losses of the duct system result into the total pressure loss, and therefore is defining the pressure rise the fan needs to overcome in order to convey this, or to convey this volume flow rate in the ducting part. This pressure loss depends only on 3 things. First, it's of course the shape of the component or the ducting part. So you would agree that maybe a straight pipe has another resistance than a corner or a bend. Second is the fluid density, and third is the fluid velocity. We will have a closer look in the next minutes how we can actually calculate a pressure loss of a ducting system. So once again, the fan has to overcome these losses and this pressure resistance, and that was maybe a little bit theoretic. I would like to give you an illustration which helps you hopefully better to understand what is volume flow and pressure rise. And that picture I want to paint is if you imagine that you inflate a balloon. I think all of you did that in your life at least once. So after you inflated a balloon, this balloon has a volume. I think that's quite obvious, and you can do this within a short period of time, or it can take longer. So if you then divide this volume through the time you needed in order to inflate the balloon, that is basically the volume flow rate you provided in order to inflate this balloon. And on the other hand, you also know that there exist balloons which are rather hard to inflate or easy to inflate. So that would be the counterpart for the word pressure rise. So sometimes you need some more energy to inflate the balloon, and sometimes it's easier. So that's the correlation, volume flow rate and pressure rise, maybe a little bit easier to understand here with this picture. Okay, now coming to our next topic, how this leads to operating points for a fan and resistance curves, etc. You may have heard in the past. So that's the next main topic here. And to do so, I'm sorry to bore you with another equation, but that's an important equation. That's the energy equation, which was found by Daniel Bernoulli. He was a Swiss mathematician and physicist, and he found that if you imagine this kind of vessel or jar here, which could be filled with water, that the total energy or pressure at point 1 is exactly the same as the total pressure in point 2. And this total pressure can be divided into 3 different parts. That's the static pressure, for example, the atmospheric pressure, a dynamic pressure, and you see there is the influence for dynamic pressure is the density and the velocity of the fluid, and a hydraulic head. So it takes care of the let's say potential energy of the fluid. So once again, the definition of this energy equation is that the energy in point 1 is exactly the same as the energy in point 2, and you will agree with me that the velocity in point 2 might be higher than in point 1, but on the other hand, the hydraulic head in point 1 is higher than in point 2. So there's always this balance within these three kind of different energies here. So that's the energy equation without losses. So in an ideal world, you know, we do not live in an ideal world, so we need to adjust this equation in order to take care of the losses which occur also here in between 1.1 and 0.2. Or even if we have a look at some maybe technical plant and we want to have a volume flow or mass flow, which is now should go from 0.1 to 0.2, there occur losses in between. So the energy equation, Bernoulli's law for incompressible fluids, in this case also with losses, is now once again the total pressure in point 1 is exactly as the total pressure in point 2, but now with all the sum of the losses which occur from 1 to 2. And you see that this term has another important parameter here. It's a Greek letter zeta that is called the dimensionless pressure loss coefficient. And it's defined as the total pressure loss, for example, here between the points 1 and 2, divided by most of the time the inlet dynamic pressure. So in this case would be the inlet dynamic pressure in point 1. And this dimensionless pressure loss coefficient is constant for each and every ducting part. So let's say every corner, if it looks similar, you can make it shorter or bigger or smaller. As long as it's geometrically similar, it has the same and constant zeta value. So that's quite good for us in order to then calculate all the pressure losses in a duct system, in order to get to know what kind of pressure rise does our fan needs to provide. You may ask, okay, if that's so easy, where do I get these zeta values from? And I think there are three different possibilities. So first of all is literature. So there are tons of tables, books, diagrams where you can find different zeta values for elbows, T fittings, Y fittings, inlet nozzles, etc. So that's one possibility. Another would be you can do a CFD calculation. Oh, sorry, that was too fast. The CFD calculation in order to get to know the pressure losses or then the zeta values. And last but not least, but I put that in brackets because it's, I think, the has the highest efforts here to do experiments or measurements. Whereas, of course, I think most of the literature is based on measurements or experiments. Okay. Then this leads us to a kind of operating point. So you want to have a certain volume flow rate. So I have now a diagram here with the x-axis a volume flow rate. And that's maybe the volume flow rate you're looking for in your technical plant. And you know now all the duct system and can calculate all the pressure losses with Bernoulli's law. and then the result would be here one red point. So certain volume flow rate results with certain pressure loss, or now in this case for the fan spoken, pressure rise. And there's also now shown a resistance curve, which has a parabolic shape. So why is that? So maybe once again, this parabolic curve represents a kind of total pressure loss coefficient for the whole duct system, and it does not change if the duct system does not change. Now coming back to the question, why is it a parabolic curve? Well, if you remember Bernoulli's law, that the pressure losses are proportional to the velocity squared. And if you remember the continuity equation, you maybe remember that the volume flow rate correlates linear with the velocity. So at the end of the day, the result is that the pressure loss or pressure rise is proportional to the volume flow rate squared. So that's one important point you should keep in mind. If you do not know all the questions from the top of your head, but that is, I think, one important question, one important correlation you should always keep in mind, that, for example, if you would like to double the volume flow rate, that would result in 4 times higher pressure loss. Okay, I said that this resistance line does not change when the duct system does not change. That also means that every operating point is on this curve. So if the fan is asked to provide less volume flow rate, the result would be, of course, then less pressure rise, or vice versa here. It's just following this correlation I just talked about. If the duct system changes, I don't know, for example, you open up some dampers or doors or whatever may change in the duct system, the resistance may change. And for higher resistance or higher pressure losses, then the resistance line the result would be kind of like the blue one here, or vice versa. If you have less resistance, that would result in this green resistance line. Okay, so now it's time for our first survey here, and I would like to encourage you to participate. And the question here would be, if you have much to do with these fluid mechanics fundamentals in your everyday life, or if, yeah, that would be something new to you. So, okay, thank you for your participation. I don't know if you see the results right now or if we show them later on. Daniel, do we see the results? Okay. So I cannot see that. Maybe you can just show me. Okay, so it's basically, it happens rather rarely, or it's your daily business. So I think it's a little bit split here, but thanks for your participation. I think we will gain some information from that. So let's move on with our agenda, and now we come to the point where I would like to show you how these different operating conditions and demands of operating points can be fit by fans. And we will start right away with the performance curve of an axial fan with variable pitch. So you might know that some of our fans are able to change the blade angle during operation. So that's possible for this variable pitch fans. And before we start, or I start to show you all the lines in the performance curve. I just heard that you do not see the screen. I think we start again. Give me a second. Okay, so hopefully you see once again the screen. So sorry for that technical problem here. Yeah, so that's basically the performance graph of a variable pitch fan, an axial fan. So at the x-axis you have the volume flow rate, and on the y-axis you have the pressure rise, like before here. And you should know that this performance graph is only valid for a certain fan inlet density. So in this case, it's the value doesn't matter, but in this case it was the density of 0.85 something. And it's of course only valid for a certain fan size, meaning outer diameter and also constant speed in this case. Okay, now let's have a look at the different curves here. So start right away with the kind of greenish curves that are now curves with different blade angles. So as I just said, the fan is able to adjust the blade angle during operation, and these different lines indicate different blade angles. Then you see on the top this kind of red line, we call it stall line or surge line, and it's literally a red line, so this should not be crossed, meaning that operating points should not be above this line. So the result would be high vibration, instability, and until maybe also fan failure at the end. So that's a line you should not cross. That can be dangerous. So no stable operation is possible above this line. And the blue curves here, which look like circles or ellipses, represent lines with constant efficiency. So I will give you the introduction of what is efficiency in the next few minutes, but yeah, that's how it looks like basically for an axial fan with variable pitch. And now coming back to the question, how can the fan now deal with changing resistance or operating conditions? Well, if you, for example, are interested in this kind of volume flow rate here, I know the value might be something about 400, and the resistance curve is like this, the black one, then it's this kind of blade angle. But if now the resistance changes, let's say it decreases, so we have the green curve. So for 400 volume flow, 400 cubic meters per second, we would need to adjust the blade angle accordingly. So that's one way to control an axial fan. Having a short look at a centrifugal fan. So I picked here now a centrifugal fan with either in inlet damper control or inlet vane control. It looks quite similar. So in this case, you have blue curves which represent different angles of this vanes here, and the red lines now are the efficiency lines. And you see that these different operating points can be operated at different vane control angles. So, I mentioned now the word efficiency several times, so it's now time to give you the definition of what is efficiency. And it's, once again, you may have heard that before. It's the ratio of the usable power, so it's the power you can use, divided by the power you put into the system. I think that's may not be something new, but it's also then obvious that efficiency can only reach numbers in between 0 and 100%. So that's an important parameter in order to characterize our efficiency or the performance of our fan. If the energy transformation is done quite efficiently, or if there are a lot of unnecessary losses, maybe. Okay, that is now leading to the next question. So I would encourage you once again to participate. And the question is, if you would like to know more about different fan types or control mechanisms. So that was quite short for today, but maybe depending on your answers, we can dive into that a little bit deeper in a further webinar. Okay, seems like you're quite interested in, so more than 50% are looking forward for some more information. So thanks for your answers. Okay. So then we move on, coming now closer to the end, where I would like to talk about optimization potentials, starting with the fan and then coming to optimization potentials for duct systems. I here only picked, once again, due to time issues, actual fan types. And starting with the fan itself, of course, what can we do in order to optimize the pressure ratio or the pressure level? That's, of course, a different plate type. So TLT has several plate type in its portfolio. And on the right-hand side in this diagram, you see some of them. It's not all of them, but some. And you will see that what you see is now basically the store lines of each and every plate type in this case. And you see that by changing the plate type itself, we can adjust to different kind of pressure levels, or then also, of course, can change the influence on the efficiency. That's not everything. Of course, you could also imagine to have only a fraction of the blades installed, so maybe half-bladed or three-quarter bladed. That a special case would be over-bladed. So when can that be helpful? Well, that can help if your plant has different expansion stages. So for example, if it starts with low pressure losses and later in the final stage you have higher pressure losses, then you may start with half-bladed fan and then install later on the other half of the blades. So that could be an efficient way to operate your fan with different kind of demands here with respect to pressure. Okay, another parameter which is important and I would like to introduce is the hub to tip ratio. So the hub to tip ratio is basically the definition. Yeah, it's the hub diameter. That should be an actual fan with the hub and the plate mounted here. And of course, you have the short diameter, and the hub to tip ratio is the ratio of these two diameters. And for isoenergetic, so free vortex blade types, the influence on the of the hub to tip ratio on the pressure level is basically that for higher hub to tip ratios, the pressure increases as well, and vice versa. So by changing the hub diameter, for example, or the outer diameter, or both at the same time, we can adjust the hub to tip ratio and therefore adjust to different pressure levels. Another parameter which can be optimized is, of course, the chord length of a plate. So what is the chord length? If you now have a section through the plate, that should be shown on this graph here, on this picture. The chord length L is basically the length of the leading edge to the trailing edge of this foil or plate. And here, once again, the correlation is the longer the plate, the more amount of work is it capable of providing, and therefore the pressure is can increase and vice versa. I should also mention now a disadvantage. If you change chord length, of course, the blade becomes heavier if you elongate the blade. So you need to take care of the mechanical problems which might occur through elongation of plate of the chord length. Okay, next survey question would be if your operational requirements change. So do you have changing requirements in your technical plant, and if so, how often or in what way does that change? Okay, so it's top answer right now is that you experience some difference between the planned and the actual operation conditions. That's also nothing new to me, but good to see that you have the same impression, and also some operating requirements will change in the near future. So that's also thank you for this frank answers here. So that may raise the question, okay, do we have some potential in order to optimize your duct system or the fan you're operating? Speaking of that, I would like to talk about what can we do, or what did TLT in the past for duct optimizations. And I would like to start with one critical parameter, which is a performance killer, and that's swirl. And I can give you an example of that. So we were asked, or our customer was claiming, well, our centrifugal fan here is not operating perfect, so it's lagging pressure rise and especially efficiency, so the shaft power was too high. And then we did a CFD calculation of that, and you see now the duct system of the suction side. So there are several bends without any guide vanes, etc., and rather bad, in my opinion, rather bad transition piece from circular to rectangular to the suction box of our fan. And the result of the CFD calculation was, now what you see here, you see the colors represent different velocities. So blue is low velocity and red is, of course, high velocity. And whenever you see this kind of blue areas here, this indicates flow separation. But what is flow separation? It's basically that the flow cannot longer follow the outline of the duct system, and that leads to additional pressure losses. And in this case, it also led to a kind of inhomogeneous inflow condition to our fan. And this then led to a massive swirl in front of our impeller, which caused then an efficiency drop and also pressure drop of about 25%. So that was, of course, a huge amount here. So if the duct system would have been a little bit, let's say, optimized, or if the separation areas could have minimized, I think the fan wouldn't have swirled in front of the impeller and then would have operated better. So at the end, I do not have the slide now, but we optimized that and could fix it by optimizing the duct system, basically. Okay, another example is now a discharge side of, I think it was a power plant here, where you have the discharge side of 2 axial fans. So that's the basically the interface of the fan diffuser and the duct of our customer. And you see once again here some overspeeds and maybe flow separation, and it's not that perfect. And we were asked to optimize this ducting system. And now you see the difference between, on the left-hand side, the original one and on the optimized one. It's still not perfect, I should say. And that's sometimes a little bit hard for us because we have a lot of geometrical restrictions given by our customers. So we are not allowed to change maybe that part of the duct, or we are not allowed to insert something into the duct. But anyway, I think the result was above 20% less pressure loss, which is good, but to be frank, not perfect, of course. Coming to another example, that's now an example of a duct system in mining or tunnel sometimes have. So in this case, it's a mining application. So you have this mine shaft coming from the mine underneath, also underground, and then you have a kind of symmetrical duct system, but a non-symmetrical operating condition. So you have the possibility to have for 2 fans, but only 1 fan is running. And so that's a little bit tricky. And to make it even worse, it needs to needs to operate also quite efficient in the other operating conditions, so meaning for reverse condition. So the fan basically is also able to convey a volume flow rate in the other direction in some special cases, and therefore, of course, the duct system needs to be optimized as well. And I should also say here once again that this kind of headband would not look like this if we would have designed it. So it's still kind of bad headband, I would say. But once again, that were some restrictions given by customer. But nevertheless, at the end, we could reduce the pressure loss of the suction side here for this fan from around about 535 Pascal to only 370, so which is about 30% less. And you now may say, okay, why are now the 165 Pascal such a big deal? Well, if you operate at a volume flow rate of approximately 540 cubic meters per second, this will result in about 89 kilowatts of additional losses or power which is lost. And if you then would say, okay, the fan is running 80% of the time in a year, that would result in an energy saving of, in our case here, more than 600,000 kilowatt hours per year. I do not know what you pay for your kilowatt hour, but I think it can be something then about 60,000 euros or dollars per year, which could have been saved or were saved here through this optimization. So I would like to say duct optimization can pay off, not only because you can reduce the pressure losses, but you can also take care of the inflow conditions to our fan in order to make the fan work in the most and best efficient way. Speaking of that, I would like to come back to this centrifugal fan I talked at the beginning. I said that there was an efficiency drop of 25% to this swirl, and that in this case corresponds to a loss in shaft power or electrical power of approximately 285 kilowatts. So I think that's a huge amount, and hopefully makes clear that duct optimization is a big thing and can pay off when talking about costs during operation. Okay, so that's now leading me to the last question, and that would be if you see potential for optimization in your plant, if you know that. Okay, most of you may not know now, but maybe an analysis would be helpful in order to understand. That's the most given answer right now, about 50%. And minor answers, or let's say 35% know that they have optimization potential. So thank you very much for participating. And that's now basically the end of this presentation. And I would like to thank you for your attention. And before we start with your questions, I would like to use the opportunity to encourage you to check out further other webinars on our homepage, and there are more to come. But now, Eric, I think you have some questions from our listeners.
Okay, yeah, thank you. I think, Florian, it was a very nice presentation. I think the most of the participants really enjoyed the whole time. During this webinar, there have been some questions upcoming. I think we will still have some minutes to go through. One of the questions was, how close to the surge line a fan can be operated? I think this is a question which is normal because you already explained it can be above and below. So
yeah, so that's a good question. So normally we have two kind of limit curves underneath the surge line, which is a kind of pre-warning, pre-alarm line and main alarm line, and they are set 10 and 5% below the surge line. So that's the recommendation from our side. So why is this 10 or 5%, well, 5% basically you should no longer operate automatically your fan, but do it manually and decrease or let's say increase the gap between surge line and your operating point. That's because every fan and every measurement system, so you need to measure your operating point during operation, and everything, measurement and manufacturing, has some uncertainties, and if you take all these into account, you will end up quite fast at about 5%. So that's a kind of safety margin here.
Okay, good. Another question was, how can the operating range to be extended to lower flows, especially in case of higher static pressure? The question is really, this is also what was in the survey. I think a lot of people have the experience that the design point is much higher than the operating points. Yeah. And so I guess the question is also how to increase the efficiency in the lower ranges that they can operate the fan.
Okay, but I just with high static pressure, so maybe the pressure level is remaining the same, but you have lower volume flow rates. Well, there are, as I told you, several parameters you can change. In this case, I think for the volume flow rate, the outer diameter is most important. So it might be possible to have maybe a smaller fan, but with a higher hub-to-tip ratio in order to have the same pressure level. But also could be done with some adjustments or with another blade type, or maybe I did not mention that in the webinar, but there are sometimes also possibilities by changing slightly the guide rates of an actual fan.
Okay, good. Another thing, I think today we have several slides regarding axial flow fan optimization, and we also have a big group of people working with radial fans. So it's what kind of possibilities we have in doing optimization in the centrifugal fan design.
Well, that's quite similar to the axial fans. So you can, of course, change the impeller. So there are different impeller types, and different impeller types provide different kind of pressure levels, for example. You can, of course, do adjustments at the fan housing, so centrifugal housing. You can also elongate the centrifugal blades or shorten them, or you could also increase or decrease let's say the width of the impeller itself. So there are quite similar optimization possibilities for centrifugal fans as for axial fans.
And I guess this we also can do not only for TLT fans, we also can do this for any kind of applications of fans in the field. So we're able to do this also for, I think, different brands.
Yeah, I think as long as we have enough information about the geometry which should be replaced or adapted.
So let's come to the last question by today, I think. If you don't have any information about the fans itself, is TLT able to make measurements or inspections at site? And based on this information, we are able to provide any kind of new designs or modifications?
Yes, we do, and we also did that in the past. So I can remember from the top of my head that we had some customer requirements that he was looking for some optimization. And before we started to have a customized optimization, of course, we had to look at the actual or current operating conditions of the fan. So we did some in situ measurements by measuring the current situation, also taking into account volume flow rate, pressure rise, and shaft power. And based on that measurement, we could then try to optimize that. And also, I did not mention that, we can validate that with model tests.
With model tests, okay. I think you now see there are different possibilities of doing optimization of your fan you have. It's not easy to explain all the details of optimization modification in this webinar. So what we still are offering, I think, after you're leaving this webinar tool, you will directly connect it to a small survey where you have the chance also to write your questions you have to TLT. You have your questions to Florian, especially for the aerodynamics. I think you can type your questions and we will go in contact with you to talk about all the issues that are upcoming. One question was also, are we able to get this presentation? Of course, you are able to get this presentation for your own information. And if you really need this, so please make a small note in the survey, then we will contact you and we will present you all the information you need. Good, Florian, I think we are now coming to the end of the time. Thank you all for participating in this webinar. We are happy to welcome you in the next webinar, I think on the TLT website, by LinkedIn, or by directly connecting to our agents and our sales managers. You will be informed in the near future about the next program, and we are happy to welcome you all here again. Thank you and have a good day. Bye.
Thank you. Bye-bye.